Okay, so yeah, the result is that the semiclassical limit. So it means that the semiclassical limit of holonomy operator and flux operator are correct, because the given the semiclassical state, the coherent state, and you compute the expectation value of holonomy operator and flux operator, you reproduce correctly the holonomy, the classical holonomy and classical flux, okay, and up to higher order correction in H bar. Yeah. So those are higher order O of T. These are higher order corrections in H bar. Yeah. So it means the semiclassical limit. When you take the semiclassical limit, the expectation value reproduce classical holonomy and classical flux. All right. So secondly, and these property also generalize polynomials. Okay. And if you consider polynomial of polynomial operators of holonomy and flux, you consider polynomials of holonomy and polynomial, or polynomial of holonomy and fluxes, and you compute the expectation value of any polynomials, and you just reproduce the same polynomial for the classical holonomy and classical flux. Yeah. So it means that the polynomial operators of holonomy and flux, the semiclassical limit, are all correct. And you can view this is a nice property of this coherent state. And secondly, you can compute the overlap function. Yeah. It relates to, and we know that coherent state for harmonic oscillator, we know that coherent states for different coherent labels, for different labels, they are not orthogonal. So although they are somehow eigenstate of annihilation operator, but annihilation operator is not a Hermitian operator. Okay, so different eigenstate, they are not orthogonal to one another. And similarly for this coherent state in Lupin gravity, so you can compute the overlap function, namely compute the inner product between two different coherent states located at two different points in the phase space, namely labeled by two different phase space points, G and G prime. Okay. And this guy, suppose G and G prime, they are very different. So if, well, this G is relates to holonomy and flux. And G prime is minus I, G prime J, half, and theta prime J, half. Okay, so this is two coherent labels and at two different phase space points. And this guy, it is exponentially suppressed. Usually we use this notation to means that they are exponentially suppressed when t goes to 0. So we call it t infinity, order t infinity. It means it goes to 0 faster than any power of t when t goes to 0. In the semiclassical limit, t goes to 0. And it means that it is exponentially suppressed. When t and t prime, they are far apart to each other. They are of finite distance. Suppressed. Suppressed. Okay. When G is not close to B prime. Okay. So namely, suppose G and G prime, well, both of them belongs to SL2C, but they are of finite distance. Yeah? And then suppose you take T goes to 0, and this overlap function suppress exponentially. Yeah. But when G is relatively close to G prime, and the behavior of this overlap function is like a Gaussian. like e to the minus t p squared plus alpha theta squared. Okay. And well, this is again as t goes to 0. Okay. So well, I mean, maybe you don't really need t goes to 0. So this is like asymptotic behavior when you when g and g prime close to each other. So when g is close to g prime, and what is delta t, delta p, and delta theta? This delta p is just the Euclidean norm of vector p. Yeah. And this is delta theta is the Euclidean norm of vector theta. Okay. And so what we mean by g is close to g prime, so it means that this delta p and delta theta is of order square root of t. So you have a t and you have a standard to say whether g is close to g prime or g is not close to g prime. So the square root of t is the standard. Yeah, and you can see that, and because the overlap function behaves like a Gaussian, suppose delta p is not of order square root of t, then this is exponentially suppressed. This function is a Gaussian, so the function is exponentially suppressed outside this regime. Okay, so this is well, in the same interpretation as harmonic oscillator is that the coherent state, it is approximately orthogonal for different coherent state labels. So when t goes to 0, different coherent states are asymptotically like orthogonal, but general they are not orthogonal. And for finite t, for finite h bar, but they are very suppose two different phase space points, they are relatively far apart. Their corresponding coherent state is it has very small overlap function. Okay? So they are approximately orthogonal, but not really orthogonal. Okay, and because they are not really orthogonal, but still you can view coherent state as some basis in your Hilbert space, but it is over complete basis, similar to harmonic oscillator. So coherent state is an over complete basis. Over completeness. Okay. So now let's normalize this coherent state. So psi twiddle is the normalized coherent state. You just divide by its Hilbert its norm in Hilbert space. You define the normalized coherent state. And for this normalized coherent state, you can write down a overcompleteness relation for a resolution of identity. You integrate of SL to C over SL to C with respect to certain measure. Okay, and psi little t g, this equals to just identity operator in the L2 Hilbert space over SU2. Okay. So this is the overcompleteness relation for the coherent state. It means that coherent state is again some kind of basis, just like harmonic oscillator, the coherent state in harmonic oscillator. But they are not orthogonal basis, yeah, because they are not. They have non-vanishing overlap function, although they are very small. The overlap function is very small, but non-zero. Secondly, you can write down overcompleteness, but this overcompleteness is associated with integral dg. It's not the summing over label of the state. It's integral, and all those states are normalized So what is this integration measure? This dg, it is this. So this is, there's a constant c divided by t to the power 3, and then then this is called a Louvre measure. So this is just the because it's just the firstly higher measure of SU2 into the theta j tau j by half. So this is firstly the higher measure of SU2, and then the usual Euclidean, the usual Lebesgue measure for P. P3T. Remember this G because, well, I have written G relates to flux and holonomy, and the integral of G is just the higher measure of the holonomy and the usual Lebesgue measure for flux. Okay, and this constant, this C is just a constant. C turns out to be 2 divided by pi plus a exponential suppressed term. Yeah, so again, a factor depends on t, but it is exponentially suppressed when t goes to 0. Okay, so this is a useful formula when we encountering coherent state calculation. Okay, so these are three most important properties of the coherent state. So the coherent state is semi-classical, so polynomial of holonomy and flux sandwiched by coherent state. It gives a classical holonomy and classical flux. And also overlap function behave like Gaussian when G close to G prime, and exponential decay when G is not close to G prime. And thirdly, you have a over-completeness relation. This coherent state serve as some kind of basis, over-complete basis in the Hilbert space. Yeah, and you can write down this resolution of identity. Okay, so these are the three most important of coherent state. And so there is a very important calculation use coherent state and to talk about the semi-classical limit of loop quantum gravity, the loop quantum gravity, the dynamics of loop quantum gravity, and talk about the semi-classics of loop quantum gravity dynamics, and ask a question whether loop quantum gravity, the dynamics of loop quantum gravity somehow goes back to general relativity or Einstein gravity in the semi-classical limit. Okay. And the answer is definitely yes, but now I'm just to sketch how this calculation works. So firstly, you need a formula for dealing with volume operator, because as we said before, and the complication because when we talk about dynamics, we need to talk about the Hamiltonian operator or Hamiltonian constraint operator and so on. And the complication in Hamiltonian or Hamiltonian constraint is this volume operator. So the Hamiltonian constraint operator is not a polynomial. It's a non-polynomial operator because you have volume operator, and volume operator has a square root. This is something I have emphasized several times. And now this, when we have this coherent state, and it provides us a tool to study volume operator. And the method is the expansion. It's a semi-classical expansion of volume operator. Expansion. Volume operator. Okay, and this expansion is firstly given by Christina Giesel and Thomas Tiemann in 2007. Okay, it is a nice tool, and so the idea is very simple. So formally, so it's just to make a power expansion to transform square root operator to a polynomial operator. Okay, so because formally, so let's do some, let's temporarily forget about mathematical rigor and do some formal expression. So remember, our volume operator located at the vertex equals to this Q operator, Q square Q operator squared and take the power 1/4. So it means, well, it is the same as absolute value of Q operator and take the square root. Okay. And Q operator, it is just right. Q operator, it is just a polynomial operator. Q operator is just you have just a 3 flux operator in Q operator, right? And Q square, of course, is also a polynomial. You just have 6 fluxes. But when you take 1/4, power 1/4, it is not a polynomial anymore. That's the complication. But now what you can do is you just make expansion for this 1/6, 1/4. Yeah, this power 1/4. And because a function to the power 1/4, it is still a analytic. Well, in most of the places on the complex plane, it is still a analytic function. The only point where it is not analytic is the branch point. Yeah. All right. So, but suppose you avoid the branch point, and you can still do the analytic expansion. So now what you do is just take square this Q square operator and minus something, minus some number. And we choose this number is just the semiclassical expression of Q, yeah, and squared, and then plus the same thing. The semiclassical, well, the semiclassical expectation value of Q. Okay, power 1/4, and this QV, it is just the semiclassical expectation. You take the coherent state on the graph, non-gauging varying coherent state. Okay, and take the expectation value. And because Q is a polynomial operator, and because of semiclassical parameter, semiclassical property of coherent state, you know that this is the result is just the Q, the classical expression of Q evaluated at the phase space point determined by G. Yeah, G determines Coulomb and flux, yeah, and you just evaluate Q, the classical Q, at that phase space point. And this is the leading order contribution, and you have higher order corrections of order h bar. And this quantity is positive. Well, unless you're looking for well, in most of generically it is positive. Yeah, and Q, of course, Q is not necessarily positive, but suppose you look at some good places in the phase space, some physical corresponding to physical volume, and at that phase space, this quantity is positive. So let's consider this quantity to be positive. All right. So now in the expression, you just minus this Q, this number squared, and plus this number squared. Of course, you did nothing. But the next step is that you okay, you pull out QV squared from the bracket. Okay. Well, you pull out square, and then you take the order 1/4, so you get 1/2. Okay. And 1 plus Q squared minus Q squared, and then take 1/4. Okay, so you get this expression, and you find well, what is this guy? Okay, well, I run out of space, and well, this guy, it is just let's call it. So this is firstly, this is an operator, right? And this because here you have a Q hat operator squared, and minus a number divided by numbers, but this is still an operator. So this operator I call it x squared. Yeah, and this x squared, this is just a quantum fluctuation. Well, suppose this is x squared, and the the expectation value of this x square, it is just the quantum fluctuation. Is quantum fluctuation of operator Q. Okay, so this is the expectation value. This is just a Q square expectation value minus Q expectation value square divided by Q expectation value square. So then this is just the quantum fluctuation of Q square of Q, and intuitively, and this is of order h bar. Okay, because intuitively, this is, suppose this is a quantum fluctuation, then it is something like order h bar, okay, and which is small. And then we can think about to expand this quantity. Remember, this is just the intuition. It is definitely not rigorous to say it is small because this is an operator. You don't know how this operator behaves. Okay, but intuitively, once you have 1 plus something, 1/4, you can always expand. Formally, at least formally, you can expand. Then you get CD 2 1 plus 1/4. Minus 3 divided by 32. I think you have coefficient and square of this fluctuation, square of this operator. Square and plus high order. Okay. All right. So now suppose you accept this expansion, and suppose you truncate this expansion, truncate this infinite series. This series, and then you transform a non-polynomial operator to a polynomial operator. So the volume operator is a non-polynomial operator, but now you write this volume operator formally written as a polynomial operator. Okay, and it looks very nice because the complication of volume operator and also Hamiltonian constraint operator is just because volume operator is non-polynomial. But suppose you can rewrite it in terms of polynomial operator, then it is very nice. Suppose everything we do is correct. It's a polynomial operator of flux. Okay, because Q is a polynomial of flux, and well, you just get power series of Q, and it's still a polynomial of flux. But the problem is whether this is correct. Yeah. And this series, how to make sense of this series? This series is just formal. You assume, okay, this operator is very small, but this is operator, right? And Q square minus number divided by number is still an operator. This X is an operator, and more problematic is that this operator is unbounded operator, and this is operator on the Hilbert space, and it is unbounded, and the eigenvalue for this operator can go to infinity. Then how would you say that it is very small and you can expand, and how you make sense these power series? It means that these power series it may not be convergent. Well, definitely it's not going to convergent in many regimes. Convergent. convergent. Well, it at most somehow it can be make sense in certain situations as asymptotic expansion. Most and asymptotic expansion. Namely, in certain situations, you can consider this operator q square minus q expectation value square divided by q expectation value square. This operator is give you contribution of higher order than h bar. Well, and this because this is something like quantum fluctuation, so this operator give you contribution of order h bar, and these give you h bar square and so on. This is something you can expect at most. Yeah. And you don't expect, and also you don't expect it is true in general. And in general, this may not be, this operator may not give you a small value. Okay. So at most, it is a asymptotic expansion, or it is a semi-classical expansion. Okay. So now the work by Christina Piso and Thomas Tiemann is just telling you that how you use this expansion, okay? And the way to how to make things rigorous, and the way to use it is that indeed, of course, indeed there's a way to use it. The expansion makes sense and can be used rigorously when we compute expectation values of, for example, Hamiltonian constraint operator. Makes sense in computing expectation values of following quantities. So for example, computing, well, most naively is to compute the expectation value of the volume operator itself. Yeah, you can use that. And a little more non-trivial, let me write all of them. Firstly, it can be used to compute the expectation value of the volume operator. Okay. And secondly, you can use it to compute expectation values of Hamiltonian constraint operator. Okay. And also the Mobilum constraint operator. And also compute master constraint operator. So these are so whenever so when you compute expectation values and this operator depend on the volume operator, and you can use it. And also you can use it to compute physical Hamiltonian operator in the reduced phase-space quantization. Okay, so usually it is used in these operators, but there is a condition, is that the coherent state label for those expectation values, for this expectation value for the Hamiltonian operator and Hamiltonian constraint, master constraint, and so on, it has to be coincide with the coherent state label here. Yeah. So these two coherent state label must coincide, because this is the coherent state label for this Q expectation value entering the expansion. So these two coherent state label must be the same. If these G is the same as G in Q expectation value. Yeah. And this Q expectation value is entering this expansion. So it means that, all right, so suppose you want to compute the expectation value of these operators with respect to a certain coherent state G and labeled by G. And then you just use this coherent state labeled by the same G to write the expectation value of Q and then conduct this power expansion. Yeah? And then you can plug in this power expansion in the formula to replace volume operator and then compute expectation value. Okay. Simplify the calculation and compute expectation value. Okay. And you can replace E hat the volume operator by the Iso-Tiemann expansion. And truncate to finite order. Truncate to finite order. Okay, so I'm still this expansion will be an asymptotic expansion, but you view that it's H bar semiclassical expansion. When you truncate to finite order, the thing you ignore, and those higher orders are of higher order H bars. So when you truncate to finite order, you ignore just the higher orders in H bar. Higher orders terms and give higher order in T equals to LP squared divided by A squared. So if you truncate the power series in finite order, you just what you ignored are higher order in Planck length. All right. So and when you plug in this result, and this is something proven by Christina and Thomas in their paper. Right, and then you use this result and plug in this power series, and what you get is actually a power expansion, a semi-classical expansion of those operators. And then you can obtain the result, and this is the result finally they got. For example, volume operator, and they just show that all the semi-classical expectation values give you a desired result, namely, it just gives you the classical function of those quantities. So firstly, the volume operator expectation value just give you the classical volume, classical discrete volume, and expectation value of the Hamiltonian constraint operator give you classical Hamiltonian constraint. So this means that it is the classical function, there's a classical quantity evaluate at the phase space point label and evaluate at the phase space point labeled by G, parameterized by G, and this G is the coherent state label. So here the point is that all the semi-classical limits are discrete quantities. So we haven't taken the continuum limit yet. and this is the same for the diffeomorphism constraint, and also the same similar for master constraint. Okay, and also similar for the physical Hamiltonian. Okay, and so so left hand side they are okay, the expectation values. So these are the expectation value. On the lattice gamma, and these are discrete. The right hand side is they are discrete classical expression, classical quantity. On the same lattice gamma. Okay, so it just shows that semi-classical limit of those operators are correct. Just reproduce the classical value. Semi-classical limit of these operators. Are all correct. Okay. Correct. Okay. And then the next task is to understand the dynamics. And so it turns out that you use this result, and also considering some other tools in semi-classical analysis, and you can prove that that's the semi-classical limit of dynamics. Yeah, and especially in reduced phase-space quantization, because over there the dynamics is very clear. You have the Hilbert space with no constraint, and you have a physical Hamiltonian, and then you use the semi-classical limit of the physical Hamiltonian operator, and you can show that the semi-classical limit of loop quantum gravity dynamics is correct. Okay. I'm not going to show you the details, but here the final result is that semi-classical limit